Good morning and welcome to today's lecture. We're going to progress from what we did last week. I did an overview of algebraic operations and how they influence basic mathematical operation. How they influence basic mathematical operation. Yes, I was saying that we'll be building from what we did last week, and I hope you've managed to have a look at what we did last week and shared the recordings. I hope you got to receive them and you went through them. So basically, algebra is a very straightforward unit. It's a very straightforward unit, and we are going to really look at how best it contributes to mathematics and how best we can use it to construct our own models for the computing field. Maybe you can confirm whether you're DCS or you're the DSC student, so that I'll be able to know who is who. Okay, you can also maybe share your camera if you can. You can share your camera if you can. Okay, noted. Okay, so today I want us to look at laws of indices. Today I want us to look at laws of indices. I did look at part of it. I did look at part of it when we were last week. Okay, I mentioned, but I realized when I was watching the video through, I realized that some parts maybe had some network issues, and the screen was not shared, or the screen was not recorded properly. Okay, so I'll begin from where the screen recording stopped, so that we can move on with some in a consistent way. Okay, so today we are going to look at the laws of indices, and because this is mathematics, I'll pause for quite a number of maybe for some minutes, so that you can also copy what is on the slide there. We're not going to run it like the theory, because you really need to write what you what is on the slide, so that you try and compare. There are some mathematics that you need to solve, so that you see whether you are able to get the concept or not. Okay. Yes, so moving forward, indices are basically another means of expressing numbers, another means of expressing numbers, and the simplification processes, okay, where the numbers are raised to a given power. So the word power, and the word index will be used interchangeably. Okay, so power and index will be used interchangeably. Will be used interchangeably. Okay, so they mean the same thing. Okay, so to work with powers, or to work with algebraic expressions that involve use of powers or indices, it is necessary that we know how to handle the powers. And that is the reason why we have what we call laws of indices. So that the same way we're going to look at laws of logarithms, so on and so forth, so that any equation or any mathematical equation that requires us to put together indices or put together terms that involve indices, then those rules will provide guidelines on how we operate. Okay, so basically we have 5 major rules. Okay, 5 or 6 major rules, because some of them will always borrow from the existing rules. So basically there are 5 major rules that we have. Okay, I'll try and zoom out my content so that you can be able to see it better. Okay, so those are the rules that we have. Those are the rules that we have. So we have rule 1. Before we explain the rules, very important thing in indices is what we call a base. Okay, is what we call a base. Okay, so a base is basically that number which we are raising to a power. So in our rules, letter A will be used as the base. Letter A will be used as the base. So when I talk about the base, you know what I'm trying to refer to. Okay, so letter A will be used as the base. So if you look at our first rule of indices, 2 things. We are saying we can translate multiplication to addition. When do we do that? If we are given 2 terms, so we can call it, this is the first term, this is the second term. So if you're given those 2 terms to multiply and they are raised to a given power, then what we need to look at for us to use law 1 or rule 1 is, do they have the same base? Do they have the same base? If they do, then the rule allows us to simplify that equation by saying we can re-express this as A and M plus N as the power. So that means if the bases are the same and the bases are raised to specific powers, if they are being multiplied, then you can factorize or you can simplify that expression as A M plus N. So when you multiply the bases, if you re-express that, you add the powers. Okay. Number 2 is division and subtraction. So how does division change to subtraction? How does division change to subtraction? If 2 terms are being divided, unfortunately, they share the same base. Fortunately, they share the same base. Okay. Then what it means, we can re-express that by subtracting the powers. So we can say A raised to power M divided by A raised to power N can as well be expressed as A raised to power M minus N. So that is division changing to subtraction. The first one was multiplication changing to addition. And those rules can be able to go back. Those rules can move back and forth. In mathematics, we'll use this arrow to show that the rules can move from left to right and from right to left. Rule 3 is called expansion of powers. Rule 3 is called expansion of powers. So it means if a number is raised to a specific power, and then the whole expression again is raised to another power, then what we do, we can re-express these two as a multiplication. So we can multiply the powers and still raise the same base to that product. Okay, so m raised to a raised to power m in brackets raised to power n can as well be represented as a raised to power m multiplied by n. Number 4. So number 3 will be we'll always call that expansion of powers. Then number 4 is a number or a base that is raised to a fractional power or a fractional index. Fractional power or a fractional index. So the indices is the plural of index. Okay. Very important. Okay. Is the plural of index. Okay. So if we have an index which is a fraction, then we can re-express that expression like this. Okay. So the denominator becomes the root and the numerator becomes the power. Okay. So we have nth root of a raised to power m. We have nth root of a raised to power m. Those rules are basically supposed to help us in simplification or solution of equations that have okay. So I'm saying number 3, I was saying we have expansion of powers here at number 3. Okay, expansion of power. So we are saying if we are given a base raised to a specific power, then the whole expression again is raised to another power, that is n. Then what we do is for us to solve this equation or for us to simplify this, then we just multiply the power. So we can as well say this equation is equivalent to a raised to power m multiplied by n, m multiplied by n. And I said the whole of that expression is called expansion of power. So what we are doing from here to here is called expansion of powers. We are expanding the powers that are given. So that will happen even if the powers have been raised in 3 tiers. That means maybe a raised to power m in brackets n, and then we have another bracket again outside here. Maybe we say raised to power p. So this one can still move across, can still move beyond 2 powers. Can still move beyond 2 powers. Then lastly, number 5 as part of the rules. Number 5 as part of the rules. So number 5 is actually what was borrowing from number 4. That was what I was saying. Okay, so you look at that, they almost look alike. You look at these ones, these two. Okay, they almost look alike. That's why what I was saying, there are about 5 rules, and then 4 and 5 are borrowing from one another. They almost mean the same thing. Okay, but differently is that this is now a negative power. Okay, so we are saying if a number is raised to a negative power, if a number is raised to a negative power, then that number can be expressed as a fraction with a positive power. So we are saying if a is raised to power negative n, then we can say 1 over a raised to power n. So n becomes positive, but the whole expression becomes a denominator. Okay, it becomes a denominator. So any negative power, we say you can re-express that as the reciprocal of the original equation, but with a positive power. So this is the reciprocal of that. So that means it can as well mean if we have 1 out of a raised to power negative n, then this one can definitely become back to a raised to power n. Okay, can as well become a raised to power n. So we can get rid of the fraction and get rid of the negative. So it's like the negative changes exchange with the fraction. So this one and the fraction will move together. Then finally, any number raised to power 0 is 1. 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 Very, very important. Very, very important. So as I mentioned, when I pause, it's your time to take the notes. Problem 10 is an example that requires some simplification based on the rules of indices. Requires some simplification based on the rules of indices. So we are saying you're given this to simplify: a raised to power 3, b raised to power 2, and c, of course, if the power is not indicated, then definitely it is raised to power 1. It's raised to power 1. Then you multiply it by a raised to power 1. I've said if the power is not indicated, it is by default 1. Then b raised to power 3 and c raised to power 5. And you're required to simplify that. So what we're going to do is basically to use the rules that we mentioned there. So we say that if there's a multiplication that is happening, we are allowed to add the powers. So you collect like terms, like what mathematics back then used. perform the necessary index operation. So like for instance here, the like terms that I have is A and A. So the first A is raised to power 3, the other one is raised to power 1. So definitely, if I organize them the way they've been organized here, it will be more easier. So here, I'll have A raised to power 4. Okay. This one I'll have B raised to power 5, because 2 plus 3. This one I'll have C raised to power 6, because of 1 plus 5. Okay, then I can put them together. This is going to be my final answer because these are not like terms. So I can no longer, these are not like terms. So I can no longer simplify that equation any further. I can no longer simplify that equation any further. Okay. Then problem 11, also a simplification process, just the same way. In fact, problem 11 and problem 10 almost look alike, just collecting like terms and then putting them together. The only difference is that this one we are now handling a bit of fractions. Okay, we are handling a bit of fractions. We are handling a bit of fractions. But you'll form or perform the same operation in problem 11 as what you've just performed in problem 12, problem 10. Okay, so we're going to look at a different scenario, unless maybe there's an issue that you want addressed there. Okay, so I've mentioned problem 11 is the same as problem 10, the concept, not the exact question. The concept is the same. Problem 12, we are evaluating now. So you simplify, then you evaluate. You simplify, then you evaluate. Because we've been given the values of A, B, and C there, the exact values. So therefore you simplify and then evaluate. Simplify, then evaluate. So the simplification of this one is going to be collecting like terms together. A and A is going to be a division, so we subtract the powers. What has been expressed here quite clearly. Okay. The same happens to B. So we're going to have A squared as the result. Then for B, we are going to have B. And then for C, we are going to have 6. That is 4 minus 2. So the minus there turns to positive. So we're going to have 4 plus 2, which is 6. Okay. Then we put up our expression together here. Then we can substitute, because we know what A is, we know what B is, and we know what C is. We can substitute to see exactly what you're going to get from there. Okay. Okay, so a different problem that we can have a look at is problem 14. 13 is the same thing as problem 12. It's just a matter of putting those like terms together, then substituting with actual values for P, Q, and R. So we're not going to go into that again. We expressed it the same way we've expressed problem 12. Okay. So look at problem 14. Look at problem 14. Problem 14. We have a slightly different scenario there. So we've been given those values, and we are told an algebraic expression of the form of this can be splitted as follows. Okay, so these are very A very important aspect, but very, very simple. Okay. Simplify that into this. So what we do, we distribute the denominator. Because it is addition, we can distribute the denominator. Okay. So if it is A plus B divided by C, we can distribute C so that each item or each number has its own denominator. Each number has its own denominator. So we'll call them terms. So these are term on its own. These are term on its own. Okay. So that's the same thing we're going to do to this. That's the same thing we're going to do to this to come to this. Okay. So we are saying we're going to distribute it into two. XY is going to operate as our divisor or our denominator. Then we can be able to simplify them the way they are. So you have two terms. So you can simplify this on its own. Okay. So x raised to power 2 minus 1. The reason we're doing that is because it is a division. So it is like x squared minus x, not minus, divide by x, okay, power 1. So if we pick x and we turn the division into subtraction, we'll have 2 minus 1. We'll have 2 minus 1. So that is the expression that we are getting here. That's the expression that we're getting here. Then we're going to have y 3 minus 1 because of the division here. The same happens to this side of the equation. The same will happen to this side of the equation, where we'll have x raised to power 1 minus 1 because it is x power 1 power 1. And then we have y raised to power 2 minus 1. Okay. Then the simplified or the final answer will be this: x y raised to power 2 plus y. Okay. So we can't add y and y because there is a multiplication in between here, between x and y. Therefore, this one cannot go together. That y and the other y, we can look at them as if they are of different form. They are not like terms. Okay. So the rule 5 is mentioned here. Rule 6 is mentioned here. Any number raised to power 0 is 1. That's why we are getting this x. That's why this x, it's we're getting rid of it because x raised to power 1 minus 1 is x raised to power 0. And anything raised to power 0 is 1. Always in mathematics, 1 can be ignored. You don't have to write a coefficient of 1. So that's why y is alone without the x on this right-hand side of the equation. Okay. So next example that might be different. So there are quite a number of examples. I'll share this content with you on the portal. Maybe you can just have a look at it on your own and see how what much more can you be able to do from there. Okay, so problem 17 present a different view, the concept of expansion of powers. Present a different view, the concept of expansion of powers. Okay, so if you look at that, then you've been given a simplification there to tackle around. There is mn being raised to power 2, and the whole product or the whole term being raised to power 3 again. On the denominator, we have m raised to power half, n raised to power quarter, and the whole of that expression or the whole of that term is raised to power 4 once again. Okay, so the instruction is given there very, very strictly. The brackets indicate that each letter is in the bracket must be raised to the power outside. This is very important. Okay, so you don't raise m to power 3 and you forget about n, or vice versa. Raise n and forget about m. That bracket shows that everything within that bracket must be applied or must face the power outside. So the power outside must be applied to everything inside that particular bracket. Okay, so this one means that m can be seen to be raised to power 1 because it's not indicated. So it's by default in mathematics. It's by default in mathematics. So if you look at what has been done here, basically it's a multiplication. Okay, so 3 multiplied by 1 is expressed here. 3 multiplied by 2 is expressed here. Okay, on the lower side or the denominator side, half multiplied by 4 is expressed there. A quarter multiplied by 4 is expressed there. Then our final expression is here after the multiplication or the expansion of powers. Then because we have like terms here, we can still re-express this one further. So m power 3 divided by m power 2, that means we'll subtract the powers. So 3 minus 2, and for n power 6 divided by n power 1, we'll also subtract 6 and minus 1. And finally, we'll get m and n raised to power 5 as our final answer. Okay, then finally on that set of rules, I want us to look at problem 20, which presents slightly a different scenario. Problem 20. So we are told to simplify that expression there, x power 2 y power half brackets root of square root of x cube root of y squared, and the denominator side we have x to power 5 multiplied by y to power 3 all raised to power half. Okay, all raised to power half. So the main interest here is these roots that are here. How do we express them further? So square root of x can be x power 2, meaning x power 2 can as well be written as root of square root of x. The same will happen to x to y raised to power 2, and we are getting the cube root. That means y is raised to 2 over 3. Okay, so the denominator becomes the root and the numerator becomes the power. I think I mentioned that in about rule, was it rule 4? Okay, or rule 4. Rule 4 says that about powers. Okay, so once you do that re-expression, you can expand where necessary. So on the denominator, what we do, we just expand the powers, 5 by half, and then 3 by half, and then we move on. Then from there, now you are ready to pick the like terms together once again. You are ready to pick the like terms together once again. So therefore, you can pick x, because everything here is multiplication. Everything here is multiplication. Pick x's together. So like this is what we have for x's. Pick y's together. That's what we have. And then give us the final answer. So we are getting x to power 0, y raised to power negative half, not half, negative a third. Okay, negative a third. Because anything raised to power 0 is 1, we can ignore x because it will be 1. So y raised to power negative a third. How can we re-express that further? Very interesting. Okay, y raised to power a third. Okay, y raised to power a third is supposed to be cube root of y. Supposed to be cube root of y. But now because of the negative, then it becomes now 1 over cube root of y, the reciprocal, because of that negative, the reciprocal, because of that negative. So far, so good. Those examples summarizes rules of indices. Those examples also summarizes rules of indices. So we've not done application, we've just done plain rules. So more examples, as I mentioned, the content that I'm using has a lot of different examples that you can view. So you can pick those further exercises and try to work on them. Pick those further exercises and try to work on them. So there's pick 1, 2, 3 and try to work on them. So the answers are provided there. So once you evaluate, you ensure that you arrive to something similar to the answers provided there. You can move on once you get the copy of that. More problems, you can just have a look at them and you let us know if there's a way we can come in to help further. Yes, so I want us to move to something else. I want us to move to something else. I want us to briefly look at logarithms because they go together, indices and logarithms, and most algebraic expressions will require that you also know the concept of logarithms. So I want us to rush through that. So let me just share a different screen for that second phase. Yes, so logarithms are very important concept in mathematics too, and closely related to indices. Okay, closely related to indices. So the use of a calculator has really changed a lot of things. So nowadays, most of these concepts are not really powerful as they used to be before. Okay, but we are connecting it to the concept of indices or the power that we've just looked at from the previous chapter, or from the a few minutes ago. Okay, so where you cannot perform or the rules of indices cannot work, then we usually work with logarithms. Okay, so what is this logarithms? Consider that expression in index form. 16 is equals to 2 power 4. Okay, 16 is equals to 2 power 4. We've known how that is expressed. Okay, so how do we make use of logs to re-express this? Remember the concept of the base. Okay, remember the concept of the base. So if you're given 16 is equals to 2 raised to power 4, okay, in form of logs, our answer, which is 16, okay, our answer, which is 16, if we introduce logs, we'll call it log 16, okay, then base 2 is equals to 4, meaning the base raised to the index gives us this. So we say log 16 base 2 is equals to 4. And this is how it's read. You can read it as this. Log to the base 2 of 16 equals to 4. Okay, so you can see the close relationship between indices and logarithm, a very, very close relationship between the two. Okay. So the two statements, this and this, are of equivalent weight or equivalent value. Okay. The difference is that they've been expressed in log forms, and the other one has been expressed in index form. That's how we're going to express our log. So once you get you understand the concept of indices, trying to understand the concept of logs is going to be quite an easy process. It's going to be quite an easy process. Okay. So the same happens here. The same happens at this particular point. So this is the general expression of what a logarithm is supposed to do. So in general, if a number y can be written in form of a power x, then the index x is called the logarithm of y to the base of a. Logarithm of y to the base of a. Okay, so because it is equal to, so it is the logarithm of y to the base a. So that's all generally what logs are all about. That's generally what logs. It is another way of expressing indices. Okay, in mathematics is so interesting that we have quite a number of ways of doing one or two things. You can follow so many ways to achieve different objectives. Okay, so we have two types of logs. We have two types of logs. We have the common logs. These are the logs that you really know, that you really are aware of. Okay. Then we have what we call the natural logs, or what mathematics will call Niperian logs. So common logs are normally the ones that we deal with in our day-to-day operations. Even the calculators are organized in form of natural, in form of common logs. Okay, so they are the ones you and me are very comfortable working with. Okay, so they are expressed in form of a number. I'll call it a number. Okay, there's 10. So you can press it from the calculator very fast and be able to get it out. But there is logs that we call natural logs that do not take the base 10. You cannot compute them from the calculator. Okay, So we normally say they are raised to the power, or to the base, not to the power, sorry, to the base e, okay, the exponent, to the base e, which is naturally a constant value in mathematics, is naturally a constant value in mathematics. Now, so the logs that are raised to, have a base e are not really of interest to us at this particular level, okay? We are not interested in deep knowledge about logarithms. Therefore, natural logs, especially to the base of the exponent, is not going to be of interest to us. But because you've studied the topic of logs, you must know that two types of logarithms exist: natural logs and the common logarithms. Okay, so natural logs is raised to the base of e, and we also write them as this. Okay? This is also an expression for that, so it's abbreviated as that. Okay. So if you are to be interested on them, then we'll move to chapter 14 as the book suggests, which is not going to be the case for us. Okay. So we're going to derive the laws of logarithms from the laws of indices, and you're going to see how easy or how direct it is, because you already know the laws of indices. So a bit of a recall there. Just trying to check if you understood the relationship between indices and logarithms. Okay. So evaluate log 9 base 3. Log 9 base 3. So we are looking for the answer to that. Okay. So how do we do that? We need to convert this. We need to convert that into an equivalent expression, or an equivalent representation in index form, which we get 3 raised to power x is equals to 9, where x is the value we are looking for. Okay, then you can raise the two into the same base and equate the powers. So you just cancel the bases, and then you say x is equals to 2. Okay, so that is just the relationship between the two. That is just a relationship between the two. The same happens with log 10 base 10. Okay, the same happens with log 10 base 10. Okay. So the other examples will be expressing the same. So I'll go to a unique example that is expressing something different, but you can pick example 1, problem 1 and problem 2, just for your own, just to try and check your own understanding on as far as the logs are concerned. I said the problem on problem 3 still we're just talking about the same thing. So maybe when I pause and you see something that you need explained further, you can raise it. Okay, so we can move on to, so there are similar problems that require such kind of solution from here. There are similar problems that require such kind of solutions. Yeah, maybe of interesting you can look at problem 9 and have a look at problem 9 and see how the negative has been re-expressed there. See how the negative has been re-expressed there. So log x base 5 is equals to -2. Then you can re-express that in index form, and you know well what happens if a negative power is brought into the picture. So let's look at laws of logarithms. They are all derived from the concept of indices. Multiplication changes to addition, division changes to subtraction. A log of a number expressed in form of a power how we handle the power, and so on and so forth. So law 1 is multiplication of two numbers expressed in form of logs. And to mention here is that when we're handling logs and it's not indicated here, we assume it is base 10 for mod logs. We assume it is base 10. Okay. So the rule number 1 is multiplication of numbers. So if we multiply numbers expressed in log forms, we can open up the brackets and the multiplication changes to addition, but we distribute the log for both the terms A and B. Okay. So that's rule 1. That's rule 1. So a fact check is there. Log 10 is equals to 1. So they are distributing it into 2. Log 5 plus log 2. So that is like you've written log 5 times 2. That's similar to log 10, okay? You multiply 5 times 2. But you can re-express this one as log 5 plus log 2. If you get these ones from the calculator, because we are assuming it is base 10, then you'll be able to get a 1 from here. So that's a fact check that is provided there. Rule number 2, or law number 2, is division. Okay, so when two numbers are divided, for instance, A divided by B, and expressed in log form, you can as well redistribute or open up the bracket and replace the division with a subtraction. Replace the division with a subtraction. So a check is provided there. Check is provided there. So you get the specific logs for 5 and 2, then you subtract, and you're approximately going to arrive at the same answer. You're going to arrive at the same answer. So that's another law that relates to logs. Division changes to subtraction. Division changes to subtraction. Then 3 is about power. 3 is about power. Log a raised power n is equals to n log a. So see how the power shifts and become a coefficient. Okay? See how the power shifts and become a coefficient. So as well, you can also verify that using a calculator. You can also verify that using a calculator. So those are 3 very powerful rules in logarithms. Those are 3 very powerful rules in logarithms. We also have rules that are very powerful in logarithms, but they borrow from the basic ones. Okay, they borrow from the basic ones. So once you get the basic ones right, the other ones will just come into play if a question arises. For instance, we have a law that you can introduce a common base. Okay, so like maybe for instance, you're given for instance, you're given log 2, log 4 base 2, you can introduce a common base for this one, and you have log 4, okay, divide by log 2. So all of them, you can say they are base 10, okay, base 10. So you introduce a common base, and then you can be able to re-express that. But now that is just part of the mathematical interpretation that comes in with the different questions that are there. But the 3 main important ones are the power, the subtraction one, or the division changes to subtraction, and the multiplication changes to addition. Okay. So there are problems that can be sorted out using those methodologies. There are problems that can be sorted out using those methodologies. I'll move to problem 14, for instance. I'll move to problem 14, for instance. Problem 14, where we have log 64 minus log 128 plus log 32. Okay. Several rules can be applied there. Several rules can be applied there to allow us sort out this. So we have 3 rules. We can apply the relevant ones to simplify that particular equation. So you can see, because it is simplification, you must look for that rule that is going to make that equation as light as possible. Okay. If you try the multiplication one and the division one, slightly it's going to be a bit complex for you. You're going to make the content or the equation more bigger compared to the way it is. So therefore, it means because those numbers, you look at them, you can see that they're numbers that can factor one another. Okay, they're numbers that can factor one another. Okay. So therefore, it means that using the power can be able to slightly make the work a little bit more easier. Okay, can make the work a little bit more easier. So you can re-express 64, 128, and 32 because they can factor one another into the same base. Okay, so the smallest base, of course, is 2. Okay, so you can express them into those bases. Then rewrite the equation with the logs, with the powers, and with the new bases. Okay. Then using the third rule of powers, you can retransform the powers to become coefficients. Okay. And because we are all talking about log 2, log 2, log 2, these are common terms, or they are similar terms. And therefore, it means the coefficients can be added together and subtracted together. So where there's subtraction, you can subtract. Where there's addition, you can add. So 6 minus 7 plus 5, we get -1 plus 5, we get +4. So we'll have 4 log 2. That's one way of simplifying those equations. That's one way of simplifying those equations. Okay. Yes. Any question so far? So good. Any question? Any question? Any question? Okay. So if there's no question, we can stop there. I'm going to upload the notes. You can have a look at them on your own. The notes I'm using are very straightforward, well organized. Therefore, it will be so easy for you to follow up. So I'm going to post the notes, including the remaining content of logarithms. You can have a look at them, raise any questions next time so that we can move to something different when we meet next week. So the remaining time, you can take that to have a look at the notes. We can discuss on the portal. There is a forum that I'm going to add under the notes there. You can post your question, your colleague can answer, or I can chip in as necessary. Okay. Yes, so if there's any question, kindly post your question so that I can help you where necessary. Remember, this is not face-to-face learning, so I'll not be able to know where exactly to plug in on a personalized way. So it is upon you to raise issues so that we can try and address them as much as we can. Yes, so kindly confirm, Donna had confirmed she's a DCS student. The rest, kindly confirm your course. Confirm your course and your campus, okay? I need to know who is a TRC student, Thika Road campus student, and maybe they are town students. I need to know the numbers so that I plan for that, because the sessions should be different, okay? So just confirm your campus. Okay, thank you for today. Thank you for today. And you're free to exit unless you have a question. You can use the video, share your camera, and you can ask the video with the audio. Yes, Moing, the forum is, the discussion is recorded. It will be available on the platform at about 10 or so minutes. It will be available on the platform after 10 or so minutes. You can have a look at it. But now the recorded one, I doubt if it has really good quality because of the breaks that we are taking as you put up some notes. But the notes are going to be available there, so you can go through the notes as well. Okay, thank you. If there's no more question. The previous content is also there. I don't know. You let me know if you cannot be able to access them. But but the previous content, I expect them to be there.
You are currently the only person in this conference.